we are just kind of reviewing some of our algebra skills in chapter 1. But, you know, all of these skills that you're going to see, they're going to kind of be bumped up to the next level, just so you're aware. So let's look at this first one. It says, find the expression describing the line segment between 5, 2, and 3, negative 4. So here's my suggestion on how to do this problem. If you want to find any sort of linear equation, I think the most effective tool is to use y minus y1 equals m times the quantity of x minus x1. We're going to use that again and again and again in this class. So I think that's the most effective tool to find an equation of any, whether it's a full line or a line segment. Next, so the first step is to find your slope. The second step is to find your equation. In this one, because it's in a line segment, there's a third step. We have to find the inequality or the interval notation. Because this segment starts at one place, stops at the other. Okay. So the first step we're going to take is to find our slope. So remember, that's just y2 minus y1 over x2 minus x1. So the point described, I would suggest labeling them x1, y1 and x2, y2. Now remember, with slope, it doesn't matter which one you choose to be x1, y1 and x2, y2. You pick, I don't care. Just be consistent when you plug it into the formula. So y2 in this case is negative 4. Y1 is negative or 2, so we're going to be subtracting 2. And then x2 is 3. We're going to be subtracting x1, so subtracting 5. So that's negative 6 over negative 2. Negative 6 is divisible by negative 2. For slope, leave it in fractional form unless it reduces perfectly. So our slope is 3. So if I just said find the line between the points, we know already that it's y minus 2 equals 3 times x minus 5. So that's all you would have to write down. So that's the line. But the question is describe the line segment. So if we look at our points, which is our x value that's the smallest? 3. Which is our x value that's the largest? 5. So all we can say to make it a line segment, if you just add on the little extra third thing I was talking about, is that our x start at 3, stop at 5. So you restrict the domain of the line, so it starts at the lowest, 3, stops at the highest, 5. So do I need this equation taken down further? I do not. That's perfect the way that it is. No, the y's will restrict themselves. So by just doing the x's, you'll end up restricting those y's. So if you just tell me what the new domain is, you make it a line segment instead of a full line. In Desmos, so let me show you how to check your work. Okay, please tell me if this is right. It was y minus 2 equals 3 times the quantity of x minus 5. Was that it? Okay. And then here's a cool thing you might not have known in Desmos. We want the x's to be between 3 and 5, right? If you put a little squiggly bracket, I just got to find where that is, squiggly bracket, and you say that, was it between 3 and 5? Is that it? If you say that 3 is less than or equal to x is less than or equal to 5, look what we get. You get a line segment. Now look at the endpoints. The end should be at, was the point, what was the first point? 3, negative 4? And was our last point 5, 2, So Desmos, you can restrict domains in squiggly brackets. You actually can't put the interval notation. You do have to put the inequality, but you can get Desmos to check your work. Okay, any questions about example 4? I would prefer interval notation. If you did put the inequality that x has to be between 3 and 5, less than or equal to 3, 5, that's okay too. I just want us to use interval notation as much as possible. Am I going to mark it wrong if you use the inequality? No. But just get in the habit of using interval. I know. Yeah, you don't have to. Okay. Any other questions about example 4? Okay. Example 5. Let's practice graphing a piecewise function. So we've got this piecewise function here. Let's discuss what each piece is. First, this piece here, what is it? Is it a line, a parabola, a absolute value? What is it? It's just a line. Okay, so let's call this one, I'll write it in red, y equals, and I'm going to rewrite it -1/2 x plus 3. And that's for anything that is less than or equal to 2. So do you notice our border? Sorry. I don't know how to get this to move. It doesn't move when I want it to. There we go. Okay. Do you notice how our border here is at 2? And that's the only border. My suggestion would be take, there used to be a way for me to write a dashed line. I don't know how to do it. Anyway, take at 2 and put a dashed border. So that dashed border is just going to give us an indication as to where our function lives. So we want to graph the line y equals -1/2 x plus 3 less than 2. Now you need 2 points to make a linear equation. Okay, you need 2 points. My suggestion would be for the one that is on the left of the this line, because the y-axis is there, why not just do the good old start at the y-intercept of 3, go down 1/2. Now we're going to hit the line. This means that we can be equal to the line. So we can actually down 1/2 touch the border. And then I would go in the opposite direction of my line, because remember that line lives to the left of -2, and then I'll make my line. Okay. Now let's talk about the next piece. What kind of figure is this? What kind of thing is that? 2x minus 5. What kind is that? It's a linear function as well. So it's y equals 2x minus 5. Now that graph lives to the section that's greater than 2. So it lives over here. So we can't do the trick that we start at -5 and go up 2 over 1, up 2 over 1. We could, but my suggestion instead is to, for a linear function, you only need 2 points. So why not plug in the border? Am I allowed to equal the border? No, so that's going to be an open circle. And then plug in something bigger than 2. So why not 2 and 3? Now you can do start at -5, go up 2 over 1, up 2 over 1, and then start drawing the graph from there. But my suggestion would be, why not plug in the things you need anyway? So if I plug in 2, I get 4 minus 5, or -1. That's going to be an open circle. So let's over here at the point 2, -1, put an open circle. And then let's plug in 3. That's 6 minus 5, or 1. So let's put a little point there. And then we can keep following the slope from there. Linear functions, you know lots about them. So don't make them harder than they have to be. So you'll notice that our original function here is to the less than or equal to 2. That's why it has a closed-in dot. This one has an open circle, bless you, and is greater than 2. Any questions on graphing that piecewise function? That makes sense, kind of, maybe? Okay. Let's talk about symmetry for a moment. You may recall that an even function has y-axis symmetry. This is an even function. You can fold it across the y-axis and it will have a perfect image on the other side. And in this particular case, f of x equals f of negative x. So if I plug in negative x into the function will look exactly like it started. Odd functions look like this one. This one has y-axis symmetry. This one has origin symmetry. And so an odd function has origin symmetry. So remember what that means. If you have origin symmetry, you could put a push pin in the center of the origin. Like a pinwheel, you should be able to turn that 180 degrees and your picture will look exactly like it started with. The way that I also think about it is if I took a point on the graph and I flipped it across the x and then flipped it across the y, I should land where I started with. If I flipped it across the y, then flipped it across the x, I should land where I started with, okay? That's origin symmetry. The way we can check it algebraically is if I plug in negative x, I get the opposite of what I started with, because it's a flip-flip. A negative x makes a negative y, so it's a flip-flip. Last year, we touched upon symmetry just a little bit, not a lot, but it is important that we know it. We're going to be graphing even more complicated graphs this year than we did last year, and so symmetry can help you because you can focus on graphing, like if it was an even function, you could focus on graphing something to the left of the y-axis, and then you know there's an image that's a perfect match on the other side. So it just allows you to check your work, do less work. Yeah. Okay. So let's algebraically check if the following functions are even and odd, and let's then mention what symmetry they do or do not have. So let's look at our first one here. The way that you check it algebraically is you stick in negative x and you see what happens. So all of the x's in parentheses become a negative x. And then you just algebraically simplify it as much as possible and see what happens. If when you simplify it, it becomes exactly what it was to start with, it's an even function with y-axis symmetry. If it is the opposite of what you started with, like if you multiplied -1 by what you started with, then it has origin symmetry. If some of the pieces change and some of the pieces don't, it doesn't have anything particular. Okay, so on top, that negative inside of a square is going to become a positive. On the bottom, that negative inside of a fourth is going to become a positive. So you'll notice that it is the original. So when it matches the original, that tells you, that tells us that it is even with y-axis symmetry. How could we check our work? Well, that's where Desmos comes into play, okay? I would check your work in Desmos. So if we go back to Desmos, and if we put in x squared over x to the fourth plus 1, it should be a graph that I could fold down the line y equals 0. No, x equals 0, the y-axis. I should be able to fold it across the x-axis, and there should be an image on both sides. It's a perfect match. Think of a butterfly, okay? I can fold it down this line. It's a perfect match. So it's like a butterfly down the middle, okay? So you can check your work in Desmos. Let's now do B. So again, we're going to stick negative x in for all of the x's. So we're going to get negative x times the absolute value of negative x. What does the absolute value of a negative do? It makes it positive. So we can rewrite this as negative x times the absolute value of x. That negative inside an absolute value doesn't do anything. Now the negative on the outside does, right? So would you say that this is the opposite, if I could write the word opposite, of the original? It's like I multiplied negative 1 by the original. When that's the case, it's odd with origin symmetry. So if it's the opposite of the original, it's going to be odd with origin symmetry. Now let's go ahead and check what that looks like in Desmos. Okay, so let me put that in Desmos. So if I look at x times, oh, I saw the absolute value. Where was it? I saw the absolute values. There it is. The absolute value of x. See what happens. It looks very much like a cubic, doesn't it? But would you agree that I could put a push pin on the center, kind of like a pinwheel? I could turn this 180 degrees. You could also see if there is a piece in the first and kind of flip piece in the third, or a piece in the second will show up a piece in the fourth. If that's the case, that's a perfect example of origin symmetry. So the graph and the algebra should always go together, or one of them is wrong. Okay, let's go back and do our final equation. So we're going to stick in negative x. We're going to see what happens. Put your negatives in parentheses, especially if there was a power on it. Now let's remember our rules of equations, or rules of negatives, I guess. If you have a negative inside of a power that is odd, it's going to become a negative. If you have a negative inside a power that is even, it's going to become a positive. So this one is going to become the opposite of, this piece is going to become the opposite of what it started to be, right? And so that piece is going to become a positive 3x cubed. Same thing is going to kind of happen here. This gives us 5 negative symbols, and then this 6th symbol turns it back into a positive. So that's going to become positive x to the 5th. So does it look like the original? No. So it's definitely not an even function. Is it like I multiplied the entire equation by negative 1? So is it odd? No. That 1 screwed it up. A constant is always going to be an even piece of the function. So if we put some pieces odd, that 1 throws it off. So if we were to throw that into Desmos, you guys are going to have to tell me what that equation was. It was 1 plus, no, it was 1 minus 3x cubed. Thank you. Minus x to the 5th. And you can see we can't fold it across the y-axis. it isn't even going through the origin, so how's it going to have origin symmetry? You can't turn it at the origin. This actually has symmetry across the point y equals 1. Not 1 screwed it up. So that's what happened there. Okay, any questions about symmetry? Does that make sense so far? Yeah, so that let's write that. That's not. Thank you. Okay, so there's kind of an example of each. So if it becomes the original when you stick in negative x, it's even, y-axis symmetry. If you stick in negative x and it becomes the opposite, or like you multiplied by -1, it is odd with origin symmetry. And if some pieces change and some pieces don't, then it is none of the above. Okay. Let's talk about increasing and decreasing. This lesson has so much to it. I apologize. And I might have even put in Google Classroom, we were going to get to 1-2 this week because I didn't realize it was only a 3-day week. So we're doing 1-1. That's it. We'll probably have to take notes tomorrow too. I'm just warning you. Okay, increasing and decreasing. A function is called increasing on an interval if the y's increase as the x's increase. The function is increasing on an interval if the y's increase as the x's increase. So let's look at the picture down below. Okay, so I'm going to move the picture up just a little bit here. Well, I'll move it up even more. Well, let's just write in the definitions and then we'll go back. Okay, a function is decreasing on an interval if as the x's increase, the y's decrease. So the x's always are increasing. The x's are always moving from left to right. If the as the x's increase, if the y's go up, it's increasing. If the y's go down, it's decreasing. If the y's are flat, like a horizontal piece, that would be a constant. So flat, constant. So let's take a look at these pieces here, and let's take a look at what's doing what. Okay. So for this section of the graph, let me get a highlighter here. For this section of the graph, so if we say for an x value from A to B, the y value is increasing. Now let's take a look from B to C. From B to C, the y values are decreasing. And then from C to D, we're going uphill again. So okay, so let me say that again. From an x value of A to an x value of B, the y's are going uphill, they're increasing. From an x value of B to an x value of C, the y values are decreasing. From an x value of C to an x value of D, the y's are increasing. So uphill, downhill. So we are always walking from left to right. So you might recall my little math bug. he's always walking to the right when determining increasing or decreasing. So if he's going uphill, then his height is increasing. If he's going downhill, his height is decreasing. If he's going uphill, his height is increasing. The word increasing, decreasing, I tried to stress last year, always is referring to what is the height doing as I move from left to right. What is the height doing as I move from left to right? Okay, so that's just important to know that. Any questions on the increasing, decreasing stuff? Okay. Composition of functions. Remember, this is the same as f of g of x. Okay. So how does it work? Well, we are plugging x into the g function. We'll get an answer. That answer goes into the f function. So the key to this is always work from the inside out. Always work from the inside out. Let me see, do I have example? I'm like, do we have examples? Yeah, this lesson has so much stuff in it. Always work from the inside out, okay? So let's do that for this. And now this is going to be complicated because, okay? So f of g of h is the same as, we're going to take the f function, we're going to plug in g, and in the g function, we're going to plug in h. But if you work from the inside out, it won't be quite as complicated. So this is my suggestion, okay? Let's take and write an F, ignore it. Let's take and write a G, ignore it. And let's put our H right here. Now we're done with H. We don't have to worry about H anymore. It's where it belongs. It's telling us that we are going to go into the G function. Because remember, we're working from the inside out. So x squared goes into the G function, okay? So go to the next thing. So now we're going to go to the G function in red here. We are not going to touch f. So in this case, leave the f there. And now it's finally time to use the G function. The G function says whatever I input, I'm going to double and add 1. That's what it means. So I'm going to double that and add 1. So it's really going to be 2 times my input plus 1. And then just simplify that as much as we can. There's not much we can do, really. So we're going to get f of 2x squared plus 1. Okay. Now we are ready to look at our f function. We're going to plug this in to the f function. So it's going to go right there. Now, there might not be much we can do, but this is going to be the square root of our input minus 4. So just put your input right here. So it's our input, 2x squared plus 1 minus 4. Now, just make it as pretty as you can. There's not much we can do. 2x squared plus 1 minus 4 is really 2x squared minus 3. Now, there are times for problems like this, they'll say, what is your domain? What values work? Yesterday, we talked about what makes a fraction, or not a fraction, we did fractions and square roots. What makes a square root work? What do you know about a square root's domain? Yes. The inside has to be greater than or equal to 0. So in this case, we should realize that our domain has to be where 2x squared minus 3 is greater than or equal to 0. Excuse me. Now, that being said, eventually we're going to have to state what that is. What numbers is that? Right now, that's all we need to think about. But eventually, do you remember we did the plus or minus charts? That is something that we have to use multiple times in the class. Okay? Any questions about example 7? Okay. Example 8. So it says that we have this function, and please note, in a calculus class, they might use a capital F to designate one thing and a lowercase f to designate something different. So please get in the habit, if they used an uppercase, you use an uppercase. If they use a little f, you use a little f. If they use a big F, you use a big F. It may sound silly, but depending on what we're doing, you might need different letters. They mean different things. So be careful, okay? So they said that big F is the tangent of the quantity of 2x plus 4. So what they want you to write is find two functions, little f and g, such that if I put them together, I get big F. So all you have to think about is this. What function is on the inside? What function is stuck on the inside of something? 2x plus 4. So if this is our inside function, that's the one we're going to make g. Whatever is stuck inside is going to be g. Whatever is stuck on the outside is going to be little f. Okay, now how do we write it? Well, g is the easy one. G is just exactly the inside function. F is going to be the outside function, but simplified more. So it's just going to be that tangent of x. And here's how we check. What we want is we want f of x to be f of g. Or if I take the f function and I plug in g, if I take the f function and I plug in g, I should get the original. That's what they're looking for. Okay, so let's do that. Let's check our work. So here's the answer. There's our answer. Let's do a little check. What would f of x be? Well, f of x is f of g. So we're going to take our f function and we're going to plug in g. What's g? We made it 2x plus 4. So if we put 2x plus 4 as the input, isn't it going to go right here? Isn't that where we wanted it to go? So that's all it is. Don't make this harder than it has to be. So it is just the tangent of 2x plus 4. So it worked out. So all we're doing is pulling apart the function. We're going to call the inside g. We're going to call the outside simplified version f. And if you put them together, you get back what you started with. This kind of thinking is going to be important. We are going to do something called the chain rule eventually. And the chain rule kind of does that undoing kind of thinking. And so this kind of helps your brain start getting used to kind of undoing, ripping apart pieces. And so that's why it's kind of important to see this now, because in chapter 3, I think it is, when we do the chain rule, it'll be important. Okay? Any questions on example 8? Okay. Oh, last example. Oh, I didn't think we were going to get through it. This is wonderful. Okay. So example 9. We did a lot of compositions and we did a lot of function stuff last year, but we didn't always rely upon the graph. So I would like to now do something with the graph, a little more abstract, more calculus based. So let's take a look at A. A says to find f of g of 2. Now, if you keep in mind, I'm going to work from the inside out, you'll be good, okay? So on the inside, it says to find g of 2. Ignore that f is even there. And I'm going to focus on g of 2. On a graph, g of 2 is just the height on g when x equals 2. That's all it is. G of 2 is just the y value when x equals 2. So we're going to go over to our graph. We're going to find the g graph. That's this one right here in blue. We're going to go to an x value of 2. And what's our height? 1, right? Our height is 1. And so g of 2, sorry, I'm not used to these new tools down here. G of 2 is equal to 1. So take out g of 2 and replace it with its height, 1. Now we're done with it. And now we focus on the f function. Remember, f of 1 is the height on f when x equals 1. So now we go to the f function. Now we go to the f function. We go over to an x value of 1. What's the height this time? 4. So the answer is 4. Does that make sense how we work from the inside out? Okay, let's do it again. Let's take a look at B. G of f of 0. Now, I never use, when I'm writing out my work on paper, I don't use the composition notation. It's not super helpful. I take out the O for composition and I replace it with the parentheses because it's easier to visualize what the heck they want. Now, you don't have to, it's just helpful. Now, remember, we're going to start from the inside. We're going to go on the f function and we're going to look, what is the height at 0? So here's the f function. Can somebody tell me what is the height at 0? 5. So this is 5. So that's just going to be g of 5. Okay. So now we're going to go on to the g function and look at what is the height when x is equal to 5. So 1, 2, 3, 4, 5, go up. Our answer is right there. What is that, 5? 1, 2, 3, 4, 5. Would you say that's 5 again? We're going to say it's 5. You know, you just guesstimate for me. Oh, you should be. Oh, that's why you guys looked at me like I was crazy. Okay. The g function is in blue, Mrs. Hot. So let's go to the g function. I was just testing you. And we're going to go to a x value of 5, 1, 2, 3, 4, 5 on the g function, which is 2. Sorry about that. I saw some blank faces there. I wondered what the heck you were concerned about. That was being weird. Okay, let's look at C. That's g of negative 6. So start on the inside. What is the height when x equals negative 6 on the blue function, the g function? Thank you. So 1, 2, 3, 4, 5. Oh, that's positive 6. Oh my gosh. 1, 2, 3, 4, 5, negative 6. What's the height? 2. Now ask ourselves, what's the height on the g function again when x is 2? So what's the answer? 1. Finally, g of f of 4. What function are we going to start with? F. What x value do we have to check? 4. So we're going to go over to an x value of 4. 1, 2, 3, 4. We're going to go up to the graph. What height are we at? 7. So this is going to be g of 7. So now we have to go to the blue function, the g function, and we have to find an x value of 7. 1, 2, 3, 4, 5, 6, 7. Does that function exist at 7? No. So the final answer here would be undefined. We don't have an x value of 7. The function is undefined there. You can write the word undefined, or you can put the little null set. That's fine by me. Any questions for example 9? We good for that one? Okay, so notes are finished. Here's your homework. See how it says solutions down here? There are no solutions yet. I apologize. The solutions will come when I make them up. So I will send them out to you probably around the due date they're due or the day after. Okay. But your job tomorrow in class is to work on these. And check the due date for me. Could somebody tell me in Google Classroom what the due date is? Check your due dates. It is marked as Friday. Oh, is that the one that's 2:59? Oh, because remember, this was Pacific time. We got to change that. Okay, so there you go.